Alright folks, we are done with page 1 of the notes. Let's jump into page 2. So page 2 starts off with a bunch of definitions. We're going to talk about one-to-one functions, the horizontal line test, and invertibility. A function f is said to be one-to-one if it matches different inputs with different outputs. That is, no output is repeated. Equivalently, f is one-to-one if and only if. Whenever f of c equals f of d, then c equals d. So the important thing I want to highlight here is this idea that is no output is repeated. So I can think of a function like y equals x squared. And let's just take a quick look at the graph of y equals x squared. If we look at the graph y equals x squared, I have outputs that are repeated. I have an output of y equals 1 at 2 different locations, y equals 2 at 2 different locations, y equals 3 at 3 different locations, etc., etc. So y equals x squared is not a one-to-one function because we have outputs that are repeated. So what is an example of a function which might be one-to-one? Well, let's take a look at this is the example I like to illustrate functions that are not one-to-one. How about one that is one-to-one? Let's take a look at x cubed. If we take a look at x cubed and we kind of know that general shape, there are no y values that are repeated. There's only one place where you get an output of y equals 1. There's only one place where you get an output of y equals 3. There's only one place where you get an output of y equals negative 2. So y equals x cubed is a one-to-one function. It fits this definition. The horizontal line test is a way for us to test graphically whether or not a function is one-to-one. And basically you take a look at the graph, and if the horizontal line intersects the graph at more than one place, then it is not one-to-one. You can see that in the line y, or the function y equals x squared. Let me just go ahead and add a vertical line here. We'll go at y equals 5. So that vertical line, and I can take that line and drag it. If it intersects the function more than one place, it's not one-to-one. So you'll notice my graph of y equals x cubed is fine, because no matter where I drag this horizontal line, it only intersects the function at one location. But the blue graph of y equals x squared, nope, it's not one-to-one because I'm intersecting at 2 different places. Okay, last but not least, we have this idea of invertibility. A function f is invertible if and only if it is one-to-one and passes the horizontal line test. So that's a fancy way of saying that a function has to be one-to-one and pass the horizontal line test in order for us to come up with its inverse. So let's do some work here algebraically to determine if these functions a and b, they're called f and h. Let's do some algebraic work here to see if they are one-to-one. And the work I'm about to show you here algebraically will not show up in WebAssign. There's no way to do this in WebAssign, but it is valuable nonetheless. So the first thing I'm going to do here is say, if f of c equals f of d, and then c has to equal d. So I'm going to check that for this function f. And I'm going to start by saying f of c equals f of d. And then I'm going to plug in c to the function on the left-hand side. So it's going to be 1 minus 2c divided by 5. And on the right-hand side, I'm going to plug in d to the function. I get 1 minus 2d divided by 5. I'm going to clear fractions here and multiply both sides by 5. That's going to give me 1 minus 2c equals 1 minus 2d. I'm then going to go ahead and subtract 1 from each side. That gives me negative 2c equals negative 2d. And then I'll divide both sides by negative 2, and we get c equals d. So yay, we just proved that the function f of x is one-to-one. And if it's one-to-one, that means we could come up with its inverse. Alright, so let's take a look. We're going to do the same thing over here for h. We're going to see if h of c, if I set up the equation h of c equals h of d, do I get c equal to d? This one's a little bit trickier algebraically, so hopefully you can follow along here. All right, so up until this last step, you probably were able to follow along. I was basically just doing some algebraic manipulation, moving things around from right to left on different sides of the equation and solving for 0 on the right-hand side. So what the heck did I do here where I started moving this minus d squared up and then I factored out a -2 from negative 2c plus 2d? Well, I'm doing a strategy here called factoring by grouping. So from here on out, what I'm working on is something called factor by grouping, and this is it's not something that you might remember from Algebra 2. In fact, you may not have even covered it, or if you did, it might have been very brief. But it's a strategy I'm going to use here to show you whether or not, to prove to you whether or not this function is one-to-one. So the next thing I'm going to do is I have c squared minus d squared, and that's the difference between two perfect squares. So I'm going to write that as the quantity c minus d times the quantity c plus d, because that's how you factor a difference between two squares. And then I'm going to subtract 2 times quantity c minus d, so that part didn't change. And here's where the magic happens, folks, because we have a GCF here. We have a c minus d show up here and here. So what I'm going to do now is factor out the quantity c minus d. And what we're left with over here will be c plus d minus 2. And I believe you've heard me say this before, but the zero product property is the most underrated tool in all of mathematics. And because I use factor by grouping now, I have a product. So I can set each part of this product equal to 0. So if I do that here, I have c minus d equals 0. Oh, hold on, that should be c minus d. C minus d equals 0, which gives me c equals d. Okay, so that's the zero product property on that first factor. Now let's take a look at this second factor. I have c plus d minus 2 equals 0. Well, that means that c equals 2 minus d, and that's not c equals d, so that tells me that this function is not one-to-one. Oh, I'm going to run out of room there. Isn't that irritating? You deserve better. Let's redo that one. Not one-to-one. Okay, as I mentioned, folks, this example 4, parts A and B, a little bit of algebra to show you this idea of a one-to-one function. I'll highlight it up here. We're working through the algebra to demonstrate that. The first function was one-to-one. The second function was not, because I got two different answers. I got c equals d as a possibility and c equals 2 minus d as another possibility. Okay, so let's move on now and look at example 5. Alright, so example 5 is a type of problem that you will see in WebAssign, and we're given f as an invertible function, and it's defined by this set of ordered pairs. We're asked to identify each value below if possible. So let's first look at f inverse of 2. In order to find f inverse of 2, I have to remember that a point on the graph of the inverse is I have to switch the x and y pair from points on the original graph. So I have a point on my original graph of -4, 2. And I'm just going to write that right up here, -4, 2. So if my input to my original function f is -4, the output is 2. On the inverse, what will happen is an input of 2 will give me an output of -4. So basically what I'm looking for is, does a y-coordinate of 2 show up anywhere in my function? Sure enough, it did at -4, 2. Okay, so let's look for f inverse of 3. And again, I'm looking for a y-coordinate of 3 anywhere in my function f, and sure enough, I see it. There's the point 5, 3 that's on the graph of f. So that means f inverse of 3 is going to be equal to 5. Alright, so last example here, I'm looking for f inverse of -3. That means I need to find a y-coordinate of -3. Let's take a look. It's not that one. It's Not that one, it's not that one, not that one, or it's not that one either. So this last one does not exist. So their f inverse of -3 does not exist based on the function f that we were given. Okay, folks, it's time for to introduce a procedure to you, and this is kind of like the grand finale of section 5.2 inverse functions. This is a procedure for finding the inverse of a one-to-one function. So example 6 here is pretty lengthy. There's let me count them up, 2, 4, 6, 8. There's actually 10 different examples I'm going to show you throughout the end of this video into the next couple parts of this. But the procedure is simple. You write y equals f of x, and then you switch x and y, and then you solve x equals f of y to get y equals f inverse of x. So that might not sound obvious. I'm going to go ahead and show you a couple examples, and hopefully it'll be more obvious. The directions here say find the inverse, and it says check your answer algebraically and graphically. Verify that the range of f is the domain of f inverse and vice versa. Note these exercises and their answers can be found in section 5.2.1 of your text. But what I would like to just let you know is to check your answers algebraically and graphically. I'm gonna let you do that on your own. I don't want this video to be 7 hours long, so I'm going to let you look at graphically both the function and its inverse to see that the inverse is a reflection across the line y equals x. And in order to check them algebraically, you should check that f of f inverse equals f, and f inverse of f, f of f inverse of x should equal x. And then the reverse of that is also true. Okay, so let's just get cranking here on this first one. So I'm going to write y equals f of x. So I have y equals 6x minus 2. Then I'm going to switch the x and the y. So that's going to look like this. X equals 6y minus 2. Now I need to solve x equals f of y, which is what I have right now, so that I have y equals something. So basically I need to isolate y, solve for y. We're going to do that by, I'm going to add 2 to both sides. So that's going to give me 6y equals x plus 2. I hope you don't mind that I automatically reversed sides of this because I want the y on the left. And then I'm going to divide by 6 on both sides. So I get y equals x plus 2 over 6. And this is f inverse of x. It's just that simple, folks. So you're going to switch the x and the y. You're going to solve for y, and what you get is your inverse of the original. Let's take a look at this next one. So I have, that's not what I intended. Okay, so we have y equals the quantity x minus 2 over 3 plus 4, and I'm going to switch my x and my y. So this is going to be x equals y minus 2 divided by 3 plus 4. All right, so first thing I'm going to do is subtract 4 from both sides. Next thing I'm going to do is multiply both sides by 3. And the next thing I'm going to do is add 2 to both sides. Okay, so I'm almost done. Let's just clean this up a bit. I'm going to rewrite this as y equals, let's see, 3x minus 12 plus 2 is going to be minus 10, and that's f inverse of x. Congratulations, folks. Give yourself a little pat on the back. You just did your first two, found your first 2 inverse functions. Plenty more to do in the rest of example 6 in the next couple videos.